Dynamic programming sounds scary. It comes wrapped in intimidating words like memoization, tabulation, and state transition. But underneath it all, DP is built on one simple rule: never solve the same problem twice. In this video, we'll start with the slow recursion, see exactly where the repeated work happens, fix it with memoization, then rebuild it with tabulation. And by the end, you'll be able to look at any problem and ask the real question: is this a DP problem or not? So what is dynamic programming really? You break a big problem into smaller pieces, solve them, and save the answers. When a piece shows up again, you don't recompute it, you just look it up. That's the whole trick. DP is just recursion plus reuse. Let's make this concrete with Fibonacci. The rule is simple: fib of n equals fib of n minus 1 plus fib of n minus 2. Say we want fib of 6. Recursion happily breaks it down. Fib 6 needs fib 5 and fib 4. Fib 5 needs fib 4 and fib 3. And on it goes, branching out into this big tree, but watch closely. Fib 4, we compute it more than once. Fib 3 shows up again and again. Fib 2 keeps coming back. Every red node here is work we are repeating, and nothing is being remembered. Because the tree roughly doubles at every level, plain recursion runs in O of 2 to the n. That's the wall. That repetition has a name: overlapping subproblems. Look at fib 3, here it is, and here again. The exact same call, recomputed in 3 different places. Now imagine collapsing all of those into one calculation, shared everywhere it's needed. This is the first signal that a problem is a DP problem. If your recursion keeps asking the same questions over and over, DP can help. Think of it like a person you keep asking the same question. Instead of making them work it out every single time, you write the answer on a sticky note. The first time, you calculate fib 3 equals 2. After that, you just read the note. The second signal is optimal substructure. Big phrase, simple meaning. The answer to a bigger problem can be built from the answers to smaller ones. Fib 6 is just fib 5 plus fib 4. Fib 5 is fib 4 plus fib 3. Each correct big answer is stacked on top of smaller correct answers, like building blocks. If you can solve the small pieces and combine them into the big one, you have optimal substructure. So here's your DP checklist so far. You usually want 2 things: overlapping subproblems and optimal substructure. Fibonacci has both, which makes it perfect for learning DP. Our first technique is memoization. We keep the exact same recursion, but add a cache called memo. Before computing anything, we ask, have I solved this before? If yes, return the saved answer instantly, a cache hit. If no, compute it, store it, and then return it. Watch the tree. The first time we reach fib 2, we calculate it and save it. The next time fib 2 is needed, we don't go down the tree again, we just read the cache. All that red repeated work, gone. Here's the Python. If n is 0 or 1, return n, that's the base case. If n is already in memo, return it. Otherwise, compute fib n minus 1 plus fib n minus 2, store it, and return it. One quick note. In real code, avoid mutable default arguments. That shared memo can leak between calls. The safer version wraps a helper with its own memo inside. Same logic, cleaner. And the payoff is huge. We go from O of 2 to the n down to O of n. Each subproblem is now solved exactly once. Why do we call memoization top-down? Because we start at the top, the big problem, and recurse downward into smaller ones. Look at the call stack. Solve 6 calls, solve 5, which calls solve 4, down and down until we hit the base cases at the bottom. Then the answers come back up. As each one returns, we record it. Memo 2 is 1, Memo 3 is 2, Memo 4 is 3, 5 is 5, 6 is 8. We start from the big problem, go down recursively, and store answers while returning. That is top-down DP. Now let's drop recursion entirely. This is tabulation. Instead of drilling down from fib 6, we start from the smallest answers and build upward using an array. We seed our base cases, 0 and 1. Then we walk forward. Each new cell is just the sum of the 2 before it, left to right, until we hit our answer. Because we build from the bottom up, this is called bottom-up DP. The code is a simple loop. Seed DP0 and DP1, then for I from 2 to n, dpi equals dpi minus 1 plus dpi minus 2. That's O of n time and O of n space. But notice we only ever look at the last two values, so we can throw away the whole array and keep just two variables. That drops us to O of 1 space. Same answer, almost no memory. So memoization or tabulation, which one is better? Here's the thing, they are not two different algorithms. They are two ways to apply the same DP idea. Memoization is top-down, it uses recursion, it only computes the states you actually need, and it's usually the easiest to write once you already have a recursive solution. You just add a cache. Tabulation is bottom-up. It uses loops, it fills the table systematically, there's no recursion stack to worry about, and it's often easier to optimize for space. If you like to think recursively, reach for memoization. If you'd rather think in loops and tables, reach for tabulation, same idea, two styles. Let's leave Fibonacci behind and put DP to work on a real interview favorite, climbing stairs. You're climbing a staircase with n steps. Each move you can take 1 step or 2 steps. The question, how many distinct ways can you reach the top? With 5 steps, there are 8 different ways. Here they are. So how do we think about this with DP? Here's the key insight. To land on step n, your very last move came from one of 2 places, from step n-1 with a single step, or from step n-2 with a double step. So the number of ways to reach step n is the ways to reach n-1 plus the ways to reach n-2. Wait, that's the Fibonacci pattern again. Ways of n equals ways of n-1 plus ways of n-2. The memoization version checks the cache, hits the base cases, and recurses. The tabulation version fills a DP array. DP0 is 1, then each step adds the 2 below it. 1, 2, 3, 5, 8. Same numbers, and now you can see the structure hiding inside the problem. Here is the exact 4-step framework you should use in interviews. Step 1. Define the state. What does your function call actually mean? Step 2. Find the transition. How is the big answer built from smaller answers? Step 3. Set the base cases, the smallest answers you already know. Step 4. Choose your style, memoization or tabulation. And remember, the real thinking happens before you write any code. A quick note for the Java folks, because code clarity always shows both languages. The idea translates exactly. For memoization, you use a hash map as your cache. Check contains key, and if it's missing, compute the result, put it in the map, and return it. For tabulation, you use an int array. Set dp0, then loop from 1 up to n, filling each cell from the 2 below it. Different syntax, identical logic. Whether it's a Python dictionary or a Java hash map, the DP underneath is exactly the same. A few mistakes I see beginners make again and again. 1. Jumping to code before defining what DP of I means. If you can't say it in one sentence, you're not ready to code yet. 2. Wrong base cases. They're the foundation, and if they're off, everything built on top is wrong. 3. Confusing memoization with tabulation. Remember, top-down versus bottom-up, same idea. 4. Not checking whether subproblems actually repeat. If nothing overlaps, DP is just extra overhead. 5. Forcing DP where a simple greedy or plain recursion already works. The single most important question in DP is not about the code. It's this: what does my state represent? What does DP of I mean? Once this clicks, a lot of DP problems start looking much less scary. Let's bring it all together. Dynamic programming gets easy the moment you stop seeing it as a scary topic and start seeing it as smart reuse. 1. Break the problem into subproblems. 2. Reuse the answers that repeat. 3. Memoization is top-down, start big, recurse down, save as you go. 4. Tabulation is bottom-up, start small, build up. And 5. State plus transition plus base case equals a DP solution. If this made dynamic programming clearer, give the video a like and subscribe to Code Clarity DSA. Comment which DP problem you want next: knapsack, coin change, or longest common subsequence. This was Code Clarity DSA, data structures explained visually. I'll see you in the next one.